Hello, in the last lecture we discussed about linear array, and we actually started with a very simple concept of two isotropic elements, and we had seen that when these two isotropic elements are fed with equal amplitude and different phases, we can get the beam in different direction. For example, if the phases between the two elements is 0 degree, then the beam is in the broadside direction. That means if I have an array axis like this, so beam will be maximum in the perpendicular direction. And then we had seen that as we change the phase between the different elements, so for example, when the phase difference was 180 degree for spacing of lambda by 2, we saw that the beam, instead of being maximum in the broadside, it went into the end fire direction. And as we change the phase from 0 degree to 180 degree, we can change the beam. So we started with two isotropic elements, and then we discussed about two dipole antennas which are fed with equal amplitude and then different phases, and we had actually seen the principle of pattern multiplication. So how the dipole orientation will change the pattern. After that, we did the derivation for linear array of n elements, and what we have found out that for a linear array, the array factor is given by sin n psi by 2 divided by sin psi by 2, and the maximum value of this can be obtained when psi tends towards 0. So when psi tends towards 0, then sin n psi by 2 will be approximately equal to n psi by 2, as we know that sin x is approximately equal to x, and the denominator sin psi by 2 also becomes psi by 2. So psi by 2 gets cancelled, we left with the value of n. So the maximum amplitude of E is nothing but n. So if we normalize this particular function, then we divide it by n. So that means now this function has a maximum value of 1. Now this entire thing can be plotted for different values of n and different values of psi, and the plot is shown over here. So along the x axis, what we have psi, which is varying from 0 degree to 180 degree, and along the y axis we have an array factor, which is the normalized electric field. So let us see, if there is a single element, what will happen? Array factor will be simply equal to 1. For n equal to 2, the array factor goes from 1 to a low value of 0 at psi equal to 1 by 80. In fact, this can be checked. If psi is equal to 180 and if n is equal to 2, we can see that this value will go to 0 value. And then as n increases, so n is equal to 3, the curve goes like this. Here there is a one side lobe level. When n is equal to 4, there is a complete side lobe level, and if I look at n equal to 10, there are multiple side lobe levels whose amplitude is decreasing progressively. You can also see that as we are increasing n, so n equal to 2, 3, 4, 5, 10, if we look at the half power beam width, how do we define half power beam width? Where array factor is reduced from 1 to 1 by square root 2, which is approximately 0.707. So if we draw the horizontal line from here, so we can see, and this is the half part. In fact, the other part will be actually symmetrical to this, which will go like this here. So we are only showing the one part from the broadside direction. So we can see that the half power beam width continuously will decrease as we increase number of element. Say from starting, if we draw our imaginary line here, then n equal to 2, half power beam width will be large, then it will decrease, it will decrease, it will decrease. So which is, we also know that from array factor theory, that actually says aperture area is nothing but equal to directivity is given by 4 pi a by lambda square, where a is area. So if we increase number of element, area will increase, and that is how the directivity will increase. So half power beam width decreases means directivity is increasing. So now from here we can actually find out various things, that what will happen, where will be different nulls there. But before that, let us just look at what happens if we change the phase for number of elements. So we will take a case here where we have 4 different elements. all these elements have a spacing of d in between, and we are taking a special case of d equal to lambda by 2. So, we start with the function psi. Psi is 2 pi d by lambda cos phi plus delta. This derivation we did in the last lecture. For broadside, delta will be equal to 0. We have taken d equal to lambda by 2 and n equal to 4. So, then if we substitute this value in the function psi, so we can see that d is lambda by 2. So, that will reduce to pi, cos phi will come here, delta is 0. And then array factor is as before, sin n psi by 2 divided by n sin psi by 2. So, let us just try to plot this. In fact, we would like to plot this radiation pattern, and we can of course start with, let us say phi equal to 0, and then 10 degree, 20 degree, 30 degree, we can rotate for complete phi equal to 0 degree to 360 degree, and that takes a lot of time. So, we can do some quick things also, and that is, suppose we take a phi equal to 0. So, if we take phi equal to 0, cos of 0 will be 1. So, psi will become pi here, and if psi is equal to pi, we put the value of here, this is pi, and we put n equal to 4 here, then this function will become equal to 0. So, that is why it is 0. At phi equal to 60 degree, cos phi will be 1 by 2. So, this will be become pi by 2. Again we put here pi by 2, and this is 4. So, 4 into pi by 2 into 2 will be equal to pi, and sin pi is 0. So, again this will be 0. Now, when we take a case of phi equal to 90 degree, which is broadside, so cos 90 will be 0, psi will become 0, and sin 0 divided by 0 will be nothing but, again we have done that before, that when psi tends towards 0, this whole function will now become 1, because this is normalized with respect to n. So, we get 1. So, if we now start plotting here, so starting from here phi equal to 0, so at phi equal to 0, E is 0, so that is a 0 value. As phi increases, this slope comes, and then at 60 degree this function goes to 0, and then we increase further to 90 degree, it goes to the maximum value of 1, and then this whole trend is repeated, because the sine functions repeat itself. So, we can see from here that the half power beam width will be given over here, but the beam width between first null is nothing but, in this case 60 degree, because this angle is 60. So, this will be 30 degree and 30 degree. So, beam width between the first null will be 60 degree. Let us just take the another case now, that is a case of ordinary end fire. So, we start again with the psi, we are taking d equal to lambda by 2, and this time we want to beam maxima in phi equal to 0 degree, that is what will give us end fire array. And for this particular value, we force the condition psi equal to 0, which is for maximum radiation. We put these values over here. So, delta is calculated from this, which comes out to be minus pi or 180 degree. We substitute the value of this delta over here, we get psi equal to this. Now, again we can look at a different angles. So, at phi equal to 0, cos of 0 will be 1, 1 minus 1 will be 0. So, psi becomes 0, and if psi is equal to 0, array factor gives us value 1. When phi is 60, so cos of 60 will be 1 by 2 minus 1, so that will be minus pi by 2, and if we substitute this value in the array factor, that comes to be 0. And when phi equal to 90, cos 90 will be 0 minus 1, so that will be minus pi and 0. So, we can now do the plot same way. So, along phi equal to 0, this is maximum, and as phi increases, it is changing and it goes to 0 value, that in between it increases and again comes back to 0 value. So, if we now see the beam width between the first null, so the beam width between the first null is given by this particular angle here, which happens to be 120 degree, and that actually is much larger. If you compare this with the broadside array, the beam width between the first null was 60 degree, now it is 120 degree. So, this made a researcher think, why ordinary end fire array has a broader beam width, which results to a smaller gain. So, what can be done? So, to do that, then this concept of ordinary end fire came into picture. We will look into that, what is that concept, but let us first look at as an example first. So, here we have actually 10 isotropic elements. In this case, the distance is lambda by 4 between these elements. So, there are two plots shown over here. This is the plot for ordinary end fire array, and this is the plot which is actually increased directivity end fire array, which I have given a nickname as idea. An idea can change the life, and here an idea has changed the directivity and increased the directivity. So, what it really is happening, how it is happening? First, let us just see the example quickly. So, in this particular case, for ordinary end fire array, half power beam width is 69 degree, whereas for increase it is 38 degrees. So, one can see that there is a substantial reduction in the half power beam width, and that is why directivity increased from 11 to 19. So, how this particular thing is realized? So, for that we have to actually think about what is the phase for end fire array. We had seen that psi is given by the dr is nothing but 2 pi d by lambda, that is cos phi minus 1, this accounts for the phase. But for increased directivity we take additional phase delay of pi by n compared to the previous case. And why do we take this additional phase difference? So, that will be clear if we actually look at this plot here. So, just look at the, now we will not look at the normalized value, but let us just look at just this function here, sin n psi by 2 divided by sin psi by 2. So, in this case we have plotted two plots separately. This is the plot for the denominator, which is sin psi by 2, and psi is varying from 0 to pi. So, as psi changes from 0 to pi, at pi it will be sin pi by 2, which will be 1. So, this will vary sinusoidally from 0 to 1. What about the top case numerator here? Numerator is sin n psi by 2, and we have taken an example of n equal to 8. So, if we start with 8 here, and then as psi changes, one can actually see that there are number of sinusoidal variations, and the total you can see here, the maximum for psi equal to pi, this is 8 times pi by 2, and that will variation will be close to 4 half cycles or 2 complete cycles. So, what is the first maxima here? The first maxima comes when psi is equal to pi by n, and that we can check here. So, this is n, and if psi is pi by n, so n will cancel, this will become pi by 2, and sin pi by 2 is equal to 1, and that is the maximum value. When this term here becomes pi by 2 pi by n, then that will be the term corresponding to the 0 value. Now, if we look at the radiation pattern, let us just look at the pattern. We can see that the first beam maxima comes, and then there is a null, and then there is a side lobe coming into picture. So, now just remember this, now after the null only some maxima comes, right. So, now if we just look at this plot here, so that first side lobe level actually corresponds to this point, because it is coming after the null. So, what is this point then? Why something is maximum over here? And if you actually look at this point here, at this particular point the beam is maximum, and at this particular one here, if we just look at the corresponding value. So, here the maximum value is 1. So, sin n pi by 2 maximum value will be equal to 1, and what will be the corresponding value here? Well, we have to put psi equal to pi by n. So, if you put psi equal to pi by n, so this function becomes now sin pi by 2n. So, this is the maximum value of this particular function. So, if we normalize that with respect to 1 divided by this, so now for increased directivity end fire, normalized value is not this function divided by n, because n happens over here, that is the maximum point. This is the value which is corresponding to this maxima divided by corresponding value over here. So, if we go back and look at the same curve, so the point which we are looking at is somewhere here, where this value of the numerator is increasing to the maximum value and divided by denominator value. So, if we now start from that, so what is happening? We are starting, instead of starting from here, now we are starting from here. So, if we start from here, you can see that my null will come much faster, and if the null is coming faster, and from here if I look at a half power beamwidth, half power beamwidth will come very fast. So, that is the reason if we provide this additional phase and we start from here, my half power null beamwidth is reduced and we have a more side lobe. And over here if you look at the amplitude of side lobe is much larger than the amplitude of the side lobe over here. The reason for that is here all the side lobes were divided by a maximum value of n, whereas all the side lobes here are not divided by n, but a lower value, and hence side lobe levels increase. So, in this case that is the reason by adding this additional phase. So, this is that additional phase corresponding to psi, which is pi by n. So, if we use this particular thing, we need to use this normalized function, and that is how we can realize the increased directivity end fire array. So, let us just look at a few other examples. Let us say we want the beam maxima at phi equal to 60 degree. So, this is 0 degree, phi is 60 degree here. So, this is our desired beam maxima. So, for that we need to calculate what should be the corresponding phase value. So, psi is equal to 0, we put that condition, this is same as before, but phi has been put as 60 degree plus delta. So, we need to calculate delta, and we take a case of d equal to lambda by 2. If we do that, dr is pi and delta becomes minus pi by 2. So, that means if we take a phase delay of minus 90 degree, that means this should be fed at 0, this should be at minus 90, then this will be another minus 90, which will be minus 180, and this will be minus 270. So, if we feed it like this, that the beam maxima will be in this direction, which is at phi equal to 60 degree, and since the beam is symmetrical with respect to the axis of the array, the whole pattern is getting rotated by full conical thing. So, that is the reason we actually see the two different cones, but actually this is two dimensional, but the whole this cone is getting rotated completely here. So, what you really get is a conical radiation pattern. So, now we need to find out where is the direction of null and other parameter. For example, here one of the thing, let us just go back. So, we can find the null over here and here, but how do we mathematically calculate in which direction null is coming, and also we would like to find out in what direction minor lobes are coming, and also we want to find out what is the amplitude of these minor lobe, also known as SLL, side lobe level. So, how do we calculate these? Well, these can be calculated from the simple this array factor function. So, let us just start looking into that one by one. So, null direction. So, this is our array factor. When will be the null? Whenever the numerator becomes 0, except for the condition that psi should not be 0, okay, because there it becomes 0 divided by 0, and that is maximum value. For all other values, wherever this becomes 0. So, now we can say we would like sin n psi by 2 to be 0, which will give us the direction of null. So, this value should be then equal to plus minus k pi, that is k times 180 degree. So, k will be 1, 2, 3, k cannot be 0 because that will give us a 0 value. So, from here we can find out what is psi. So, psi should be given by 2 k pi by n. So, let us just take an example. We will take an example of a broadside array. So, delta will be equal to 0. So, we now substitute the value of psi over here, which is 2 pi d by lambda cos phi 0, and then this term comes over here, and from here we can find out what is the value of phi 0. So, phi 0 can be calculated, and this one will give us the direction of null, and all these things I have done for just the broadside. All these general cases are given over here. So, what we have, first case is general case where psi will have a delta term, delta can vary anything from 0 to 180 degree, and this one is a null direction for any length, This is an approximation which is used for a long array. Normally what it means, long array is if number of elements are more, that means if n is large, array will become large. So some approximations have been made here, and then beamwidth between the first null expression is given here. So let us say for broadside. Now if you see here it shows sine inverse, whereas what I have written here is cos inverse. Now there is nothing wrong, everything is fine. The only difference is this phi 0 is measured from the axis of the array, whereas over here gamma 0 is measured angle from the broadside. So from broadside psi 0 will be nothing but 90 minus phi 0. So cos 90 minus phi 0 will give rise to sine. So that is why the function sine is coming into picture here. And from here if you just look at it, sine inverse x will be approximated to x, that is the approximation when this term is very small, and that is obvious if n is large, this term will be small. And the same thing is done for ordinary end fire or increased directivity. And if the null direction is given here, so beamwidth between the first null will be 2 times this. So that is the expression given for this. So now let us just look at the next case, examples which we have seen beamwidth between first null and approximate array length. So we can see that as array length increases, we can see from here as array length increases, so n increases, then null direction will reduce, that means beamwidth between the first null direction will reduce. So you can see that as this is, so this is the situation for a broadside, that is the case for ordinary end fire, and you can see that for increased directivity beamwidth between the first null is reduced, that means correspondingly half power beamwidth will reduce also, and that is why directivity will increase. Now there is just one small approximation which I want to highlight, that is n d lambda is considered as approximate array length. What is d lambda? That is d divided by lambda. But in reality for linear array with uniform spacing d, array length is actually equal to n minus 1 times d. Okay. So this is just an approximation over here. So now let us see how we can calculate the direction of maximum side lobe level, and it is actually again we start with the array factor. What we really want is, now this time we want the numerator should be equal to 1, and when numerator will be 1, when n psi by 2 is equal to pi by 2, then sin pi by 2 will be 1. So if we just put that over here, sin n psi by 2 should be 1, or it can be plus minus 1. Now just to mention, see array factor is always the magnitude of the entire value. So whether it is plus or minus, ultimately we are concerned about only magnitude. So from here we can say n psi by 2 should be odd multiple of pi by 2. It cannot be even multiple, because even multiple will give us a 0 value. So this is the function how n psi by 2 is related, and from here we can find out the value of psi 2k plus 1, and once we know what is the value of psi for side lobe level, we can put now psi as 2 pi d by lambda cos phi plus delta, and depending upon the value of delta we can calculate the value of maximum radiation other than the main lobe, okay, and that will be minor lobe radiation. So this actually gives us the direction of side lobe. How do we calculate the magnitude? Well, let us say this is the array factor. All we now know that sin n psi by 2 for this case should be equal to 1. So we have put 1 over here, and now in the denominator we have n sin, and what is psi? Psi is given by this value here. So if we substitute this value, so this is the magnitude of the SLL function coming into picture here. And from here we can make a one more approximation now, that is if n is large. So for very large n we can say sin x will become x. So we make this x over here, multiply this here, so n will get cancelled, that is the array factor for large n. In fact this gives us the value of side lobe level for different values of k. So the first side lobe will be for k equal to 1, and that comes out to be 0.212, and if we take 20 log, then it comes out to be minus 13.5 dB. So we can actually see that if all the elements are fed with uniform amplitude, the best side lobe level we can get is minus 13.5 dB for first side lobe. If for second side lobe k will become 2, this value will be smaller. For third side lobe, the k will be 3, this value will become even further smaller, and this is obvious from the curve that the first side lobe level is larger. We go to the next one, then we go to the next one, we can see that the side lobe levels are decreasing, but the problem is that the first side lobe level is never below minus 13.5 dB. So now the next thing is, so what is the desired side lobe level? So in fact, in general, think about the side lobe as power going in the undesired direction. So let us say if the side lobe level is say minus 10 dB, that means minus 10 dB corresponds to 10%. So that means 10% power is going to the undesired direction. If the side lobe level is minus 20 dB, that means only 1% is going in the undesired direction. So think about a radar application which is probably transmitting 1 kilowatt of power in the main beam, and if side lobe level is only 10 dB, that means 10% of 1 kilowatt, 100 watt power is getting directed in some other undesired direction. Even 20 dB would mean 1% of the power. So of 1 kilowatt, 1% is still 10 watt power going in the undesired direction. So especially for application where we need to transmit higher power, we always try to make a lower side lobe level. Also for many satellite application, we prefer that the side lobe level should be 20 dB or 30 dB below the main beam. So the direction of the minor lobe can be obtained just from this same expression here. So substitute the value of psi and we can get the different values of the minor lobe. So this is the general case here where this is nothing but psi. Special cases are given over here for broadside, ordinary end fire. So by using this concept here, you can actually speaking find out the direction of minor lobe. So how do we calculate half power beamwidth? So half power beamwidth can be actually found in a simple way wherever array factor becomes 1 by square root 2, because this maximum value is 1. So that means now if we assume again assumption of large n, then this function here sin psi by 2 can be made equal to psi by 2. So this is like sin x by x, which is a sinc function, and we want that to be 1 by square root 2. So if we solve this one here, n psi by 2 is equal to 1.3915, and if you want to use your calculator to find out, you can actually put this value here, except that you put 1.3915 in degree, and that means you convert 1.3915 multiplied by 180 divided by pi, otherwise this value is in radian. So again for broadside we put the value of psi here, delta is 0, and from here we can calculate what is the cos phi, and this gives us the expression for half power beamwidth, which is 50.8 degree divided by L lambda. What is L lambda? It is nothing but n times d, which is length, divided by lambda, and here this expression gives all the different cases here. So here we have a beamwidth, directivity, aperture. First we will start with the linear source, which is broadside, end fire, increased directivity. Expression for directivities are given here, and here half power beamwidth expression are given. So one can see that half power beamwidth in one plane is 50.8 by L lambda as we saw, but in other plane it is 360 degree. But for ordinary end fire, half power beamwidth is same in both orthogonal plane. And here we have a case of square broadside array. That means an aperture of a square of length, total length L lambda and L lambda. So we know from aperture theory that the directivity is given by 4 pi a by lambda square. What is a for square? Is L lambda multiplied by L lambda. Similarly for square we can say what is the aperture theory says, 4 pi a by lambda square, and what is a? Pi r square. So 4 pi into pi r square reduces to pi square d square lambda, and these are the corresponding half power beam width. So, today what we have seen that different cases we studied. So, how array factor can be simply seen for the broadside array, for ordinary end fire, and for increased directivity, how normalized value of array factor changes, and then we actually look at some of the special cases of broadside array, ordinary end fire array, increased directivity, and we also found out how to calculate the phases for the desired beam direction, and then we also derived the expression for how to calculate the null direction, how to calculate beam width between the first null, then how to calculate the direction of side lobe level, and how to calculate the magnitude of side lobe level, and then towards the end we saw how to calculate half power beam width of the antenna, and from half power beam width we can calculate the directivity. Thank you very much.